Hey, George, you're a scientist.
I'm a chemist, yes.
Right, you're a scientist. So it's almost Thanksgiving here in the United States where we ostensibly are, um, as long as it still exists. We have a weird tradition of taking food that is healthy, natural, and
Yeah.
deep frying it in fats because we don't want to just eat the oil directly. That would be embarrassing. But if we suffuse the thing completely with oil, that apparently makes it okay. So around Thanksgiving, people take their turkeys and they deep fry them. And there are some very terrifying videos on the internet of people exploding their houses because they take, I think, a frozen turkey, like a frozen solid turkey, and plunge it into like boiling, I guess, like peanut oil, canola oil, oil, right? Some kind of, and then like a catastrophic explosion happens. And we talked previously because I'd asked you another time we were together, like, why don't oil and water mix? But this seems different. Oil and water do not cause these like catastrophic explosions. So what is
It'd be
it?
cool if they did.
I mean, maybe. what is it about trying to put the frozen fried or the frozen turkey in the fry oil that causes this like massive reaction?
Well, darn it, Lions, I'm a chemist, not a cookingologist. But with my very limited background and very limited expertise, I will attempt to opine to this. I feel like if you really want to discredit yourself, name a field that doesn't exist at all, you know?
Yeah. I believe you're discredited now.
Excellent. Good. So now that I've thoroughly discredited myself, listen to my opinions. So first, in order to, create anything, you must first create the universe. So first, let's talk about oil in general. Do you know what the approximate boiling point of cooking oil is in general? Like they vary a little bit, whether it's vegetable or whatever, but ballpark.
I think it's higher than water. I think it's pretty high, like 400 degrees.
You're close. Yeah.
Sorry, 300, 300 or 400 degrees Fahrenheit, which I guess would be like 150 to 200 Celsius.
Way to stick the landing. Yes. So sorry, I must have blacked out when you were talking in Fahrenheit because those are garbage units for garbage people. But yes, you're correct. Around 200 degrees Celsius, and you made the most salient point, which is much higher than water. Can you venture a guess as to why that is?
Well, so boiling, I mean, I think on the macro scale of boiling something as taking a liquid and turning it into a gas. So
that is definitionally what it is. Yes.
Okay, good. We're
good so far.
So
I think the definition for boiling is going from a liquid to a gas.
Yeah, but every once in a while you're like, well, that's how people talk about that thing. But really what it means is this other dumber thing.
Well, yeah, when it's just like oh, that's wet. It's like that specifically means it has water in it. But yeah.
I'm never going to forgive you for that because that's in my brain now. I was reading something that was like a pop science article and they mentioned like such and such a thing is dry. And I was like, but that thing is a liquid. They mean it has no water in it.
Yep, exactly.
Yeah. No, if nothing else comes away from this series of interactions, that stuck with me. So you are converting, a liquid into gas. And I would assume that the more complicated chemical bonds in an oil take more energy to break. So it would have a higher boiling temperature.
You're really close. Yeah. Like you said a couple of things that are slightly wrong. Because but you got the general idea, right? So what causes something to be in a certain state is the strength, not of the intramolecular forces, but the intermolecular forces, right? So it's not on how, for example, for water, how strongly the hydrogen is bonded to the oxygen, but how well the water molecule grabs onto other water molecules, right?
Oh, so, okay.
Yeah. So that's why things that have that are polar tend to have higher boiling points, right? So why if, for example, if you take something that's very polar, like water, it boils at 100 degrees Celsius, whereas something like propane, right, which has none of that dipole moment stuff, is a gas at room temperature, right? You got to get real cold before that. Propane, butane, pentane, octane, all of the, I think octane is volatile, but like you could actually have that as a liquid at some point, But yeah, like those molecules are getting bigger and bigger and bigger and bigger. And even though they are way, way, way bigger than water, they don't have any dipole moments, so they don't grab onto each other super hard, right? But the bigger the molecule gets, the more of what you get of hydrogen bonding between each other, where like basically it's what I think is kind of interesting. It's called an induced dipole, which is kind of neat because basically like when you've got a whole bunch of carbons strung together with hydrogens, they all share the electrons evenly. But sometimes for a split second, they won't share it evenly because the electrons are kind of moving along in their probability electron cloud, right? So in that moment when the sharing is uneven, it will induce uneven sharing in a nearby molecule. And then that one will induce uneven sharing in another one because there's that slight charge, So that's to say that bigger molecules tend to have higher boiling points, right? And if they have actual polar stuff in it, so stuff with oxygen typically, even more so, higher and higher boiling points. And cooking oil has both of those things. It has oxygens in it, which means that it definitely has dipole moments, and it is a big molecule. So most cooking oils have the formula CnH2nO, and the N is normally somewhere between 16 and 22. So it normally has somewhere between 16 to 22 carbons, right? That's a big molecule when you can compare it to like water, right? So that is why they tend to boil at a much higher boiling point, right? So big molecule. So the important thing is that it's boiling at about 2. So when you get ready to boil your turkey, right, to take the healthy thing, and to be fair, you said that we tend to take healthy things and make them unhealthy by cooking them in boiling them in oil. To be fair, we also do it with unhealthy things too. We like to put everything in oil because the minute that I heard that they are boiling, like deep frying Oreos, I was like, what are we even doing, guys?
No, dude, you can get a deep fried Coca-Cola.
What?
Yeah. Yeah.
What?
Yeah.
How does that even work?
How indeed. They take the syrup and they fry the syrup and then use that as like Yeah. Makes you want to die a little bit, doesn't it?
They were so busy trying to figure out whether or not they could, they didn't stop to think that they should.
Yeah.
Oh my God. Yeah. All right. Well, happy Thanksgiving, everybody. That's the end of the episode. We're done here. And then now you can just like cut in like me walking away from the
with the sad music from the end of The Incredible Hulk.
All right. So that's why it boils heavier or boils at a higher temperature. So I would like to diverge from my prepared remarks, and I want to talk about soda, interestingly, a little bit. So because you brought it up, so let's talk about soda.
That's fair. Yeah.
So, what happens if you shake a can of soda or beer?
You agitate out the, I guess, carbon dioxide, and so it explodes. Or pressure builds up, and then it explodes if it's a comedy.
Yes, exactly. And interestingly, when I was going through this, so like when you're shaking it, you are agitating it. But interestingly, you're doing something very specific with the nucleation sites on the side of the container. And so as I was doing this, as I was like, oh, okay, I can go through this at this part of the episode. And I said, you know what? This is actually probably entirely its own thing. So at one point we will have to do a thing on why specifically shaking a soda causes it to release the carbon dioxide that's dissolved in it. Because it's actually a little bit more complex than you're just agitating it, So I was like, oh, I'll go into that. And I was like, this is actually pretty complicated. This should be its own thing. So it'll be its own thing. But to your point, right, is that what you're doing is you're forcing the carbon dioxide out of solution and putting it basically back into its gaseous state, right? The dissolved gas. So when you have a bunch of dissolved gas in a liquid, and you can put it under pressure, right? Like that causes the gas, when you allow the gas to equilibrate its pressure, it aggressively tries to leave the solution, sometimes to the point where it explodes and flies everywhere, right? So thank you for taking that little trip for sodas. It will bear on this in every way, but I'd like to pretend that it doesn't. So finally, when we talk about a frozen turkey, we think about it as like, oh, well, like it's really, really, really cold, right? But one of the things that flesh has a lot of in it is water, right?
I've heard that.
Yeah, with liquids, I mean oils as well. There's a lot of fluids. It's moist. It wasn't you. You weren't the person that hated that word, right?
It is common for people to hate it. I'm not one of the people who flips out over the word moist.
Yeah, we might have just lost like half of our subscribers. So basically when you freeze the turkey, there is a lot of water in it. And to your point, oil and water don't mix. But when you put oil and water together, they don't explode, right? But the problem is that you're not mixing oil and water. You know what you're actually mixing?
Ice and oil.
Close. By the time you actually put the turkey in, you're no longer mixing oil and water. You're mixing oil and steam. And that's the problem. Because the oil is so hot, it immediately vaporizes the water, which becomes a gas, right? So, because it just goes right past, it goes straight through liquid, straight up into gas, because you're putting it in something that's 200 degrees Celsius, and it only needs 100 degrees to boil, right? So now you've taken a bunch of gas, water, steam, and put it at the bottom of a giant pot of boiling oil, So that then causes the gas to evolve incredibly quickly. And then for bonus points, since it starts to evolve that gas quickly and then increase the volume of the container and start to overflow, you're likely not only to get the oil to explode, but chances are that it's going to hit the heating element at some point, which then will catch the whole situation on fire.
Yeah, those are that part of the video is always the most terrifying part, right? Is the oil flying out and dumping onto the exposed flame that was underneath the pot.
Exactly. But I thought that was kind of interesting, where it was just like the reason why is the same reason why when you when you shake up a soda, it suddenly explodes is because, and why when you put just oil and water together, it's fine, because oil and water mix fine. And the thing is, it's like, oh, well, there's an exception when you're boiling a turkey. Nope. Oil and water will always just not mix. Sorry, they don't mix fine. They specifically don't mix, but they will never explode together. Oil and steam, if you said like, oh, I'm going to pump a bunch of steam into this oil, you're like, well, that'll probably explode, right? So if you, it's like one of those things where when you say what it is that you're actually doing, right? Where it's like, oh, well, a hurricane's just a lot of water. It's like, it ain't that the wind's blowing. It's what the wind's blowing,
Yes. And I like the number of basic scientific failings that are happening on the part of a person who finds themselves in this situation, right? Because to be very clear, I didn't say this at the top, but now that I'm about to say what I'm about to say, I just want to be clear, like, this is horrible, right? Like when people get seriously hurt, their house burns down, right? Their whole neighborhood burns down. Like I don't think it's funny when it actually happens to a person. I do think the circumstances that could lead up to it happening are in the sense that like people don't understand that the frozen water in the turkey, they're going to drop it quickly into the oil, and that will instantly become steam, which now has to push the oil out of the way to escape the container, which is what it wants to do. So it is now flinging oil around. And people also don't understand water displacement, right? Because they fill the vat overwhelmingly with oil, right? Maybe literally to the top, and then submerge the turkey in it. So they don't even get the thing all the way into the oil before there's just stuff flying everywhere like a horrible nightmare. Like it's, again,
well, not only
tragic when anyone gets hurt, but like funny if they don't, right? Because it's just like, oh my God.
Well, and the other thing that even if you were to do the math properly and you were to say like, hey, this turkey has an exact volume of like 5 liters. And so I've left 5.5 liters of space with, like in this 10-liter thing, I put in, 4 liters of oil. So then like I still have a liter of space left over when I'm all done. Is that that's how much volume the turkey has with the frozen water in it. But gases, expand way much and way faster, right? So all of the bubbles of gas take up a lot more space than the equivalent amount of water, which you don't consider, right? It's, so it definitely, and it was interesting because in preparation for this, I was discussing this with my wife, and my daughter overheard me, and she said, "Can we do this?" And I was like, "No."
Haven't you been listening?
The whole point is that this is a bad idea. She goes, okay. But could we do it with like just a turkey leg? Right? Like, so basically she was like
trying to bargain with you.
Well, because she was like the scale is probably the problem, right? Like that's what we're dealing with, that's the issue. And I was like, and I said, Lizzie, the issue is that if you were to have some of this oil spatter on you, it would immediately wrinkle and burn your skin with like third, potentially fourth degree burns. Because the thing is that with like, even with water, right, is that it doesn't tend to, like, it will like roll off of your skin, right? Oil tends not to, right? It tends to seep into your skin and do more damage. And on top of that is that you're not touching your skin with, and what I said to her is I said, like, when you take a bath, you know how sometimes the bath water's too hot? And she's like, yeah. I'm like, that water's like probably 50 degrees Celsius, This water is, this oil is 200 degrees Celsius. So even if you have like poured boiling water onto yourself and scalded yourself, it is way hotter than that. And the cell damage that is done by touching a heated material, to my understanding, is not linear, So it's not like it will burn twice as bad. It's like, no, it will burn 4 times as bad because it is way hotter, Yeah. So,
Yeah. I think it's, in modern society, there are not a lot of reasons an average person has to, and I'm going to choose my words very carefully here, rig up a pulley system.
Mm-hmm.
So if you're doing an activity that requires you to rig up a pulley system so you can lower the turkey into the pot of oil and get it in, without like burning yourself or having any splashback or anything, that should be a flag. That makes any reasonable person say, did I have to rig up a pulley to do this? If I had to build a simple machine from like 9th grade science class, then I should probably be more careful with this activity than I would with some other new activity, right? Like maybe you're going to make your first ever Thanksgiving souffle. And if your souffle collapses, it's really sad and it's not as delicious and you're bummed out and it could ruin the holiday if you really care a lot about the meal you provide. But you didn't have to rig up a pulley to make the souffle. The minute you said like, oh, we're going to do a fried turkey this year, I will just rig up a pulley. That's like your sign. I have to take this way, way more seriously than I normally would.
I would actually, I like what I like all of that. And I would actually make the argument that we use simple machines all day, every day, and in pretty much every aspect of our lives. But if you are creating a new simple machine at any point, any of them, like screw, incline plane, wedge, lever, wheel and axle, or pulley, any of them, just take stock of what you're doing. Because even a wedge, right? It's like all I'm doing, or an incline plane. All I'm doing is doing an inclined plane. It's like, that means that you're taking something that arguably rolls and you're rolling it up, or rolling it, any of it. Like that's
right. Yeah. At all.
Yeah. Take pause, where it's just like, yeah. So you know what I could do is I could probably create like a metal screw like system. It's like, wait. What are you doing? Stop. Probably let a professional handle.
Of all the people we know, that you and I both know, we are thinking of the same person who, if they said, I'm going to have to rig up a pulley, you wouldn't be like, wait.
Yeah. There's one person in my life.
Of all the people we know.
Yeah. Where I'd be like, they've got this. Everybody else, I'd be like, so we've considered like all of the safety, like we need to do a actual safety rundown of what we're doing. And all of this is because it's like, well, it's like, hey, what we did was we took this thing, like we harnessed the power of fire, and then eventually we found a way to take this thing of electricity and run it across a coil to against a resistor, so that way it creates heat, and then it creates this convective current, and it creates a small temperature controlled box in our home, which is a larger temperature controlled box, and we can cook this beautiful bird so that way we can eat it. And somebody's like, no, it's not tasty enough. I want to I want to create a Rube Goldberg machine so that way I can dump it into oil so that way I can cook the whole thing at once. It's like, all right, if you must, which apparently you will, like just really, do your research, run this whole situation to ground and make sure that you've really got it under control. And if it makes you feel any better, at the place that I work, they do monthly safety like briefings, and every year in Thanksgiving, it goes through, do not put a frozen turkey into oil. That is one that is specifically called out. That and deer are like be aware of deer on the road as those are the two, man. And I now I'm starting to wonder, like, people hurt by I wonder what the actual statistics are for number of people hurt by turkey explosions annually, because it's definitely more than zero.
We're not going to look that up because that'll suck a lot of the levity out of this. But that does remind me of other holiday themed questions I will have to ask you.